probablemente uno de los retos que tiene la humanidad en el futuro próximo, dado que las necesidades están creciendo exponencialmente, por todos conocidas, pero hay un segundo reto, y es que esta generación de energía sea ecológica, sea una generación respetuosa del medio ambiente y que no contribuya de forma significativa a aumentar las emisiones de CO2. Para ello, una de las posibilidades que en estos momentos que tienen un futuro más alentador y más cercano, dado que ya se está utilizando, es la generación a través de palas, de aspas, de molinos de viento, es decir, usar el viento como generador de energía. Pero esto supone crear estructuras cada vez más altas, más grandes, porque los vientos a mayor altura se mueven más fuertes, más rápidos, y por tanto tenemos como consecuencia la necesidad de nuevos materiales estructurales más resistentes que sean capaces de aguantar estas condiciones extremas de fuerzas, de medio ambiente y de otra multitud de factores, de los cuales nos va a hablar quien tenemos hoy con nosotros. Como podéis ver, es un MENG, viene de la Universidad del Océano de China, y nos va a hablar del uso de unos materiales que son muy interesantes y a la vez bastante desconocidos, son los materiales híbridos. Ella es profesora de esta universidad, la Universidad del Océano, y pertenece a un departamento de ingeniería dentro de la Escuela de Ingeniería. Sus líneas de trabajo se centran sobre todo en las propiedades mecánicas y análisis de estructuras offshore, y tenéis aquí un breve resumen de su currículum. Desde el 99, desde el año 99 es profesora en la Universidad del Océano, tanto en enseñanza como investigación. Luego estuvo haciendo una estancia en la Universidad de San Diego, en California, y durante el último año ha estado con nosotros en la Universidad Politécnica compartiendo sus saberes y ayudándonos a progresar en estas líneas tan interesantes. Yo no os robo más tiempo. Thank you very much for being here and welcome. Is your time.
Okay, thank you very much. Good morning, everyone. Thank you very much to be here. I'm so appreciated for my have chance to make presentation here. The topic of my presentation today is structural hybrid material for towers in wind energy converters. The material used here is Malecon. There are about 4 components I will talk today. Firstly, I will introduce a little bit about the basic concept of towers in offshore wind energy converters, and then the Malecon hybrid material Malecon. Then I will talk analysis ways and means. The software we used here is Sfcm and Abacus. The third part is the main part today. I will talk the results and the results of analysis and the discussions. There are 2 benchmark examples. Firstly is the panel simulation. Secondly is the tower simulation. The last part is the conclusion. With the urgent demand of sustainable resources in the world, the offshore wind energy exploration is expected to increase gradually and significantly in the world. Generally speaking, there are 2 types of infrastructure of offshore wind turbine. The first 2 pictures is a kind of fixed type. It's a monopile and jacket platform to fix to the seabed. The last 3 pictures is a floating offshore wind turbine, which aims at to be used in the deep sea or deep water exploration for the offshore wind generation. The main task structure we talk today is the towers in offshore wind converters. As we all know, with deep water exploration and higher location exploration, the tower is developed greatly from the 1926, there would be only 24 hub height. And in the 2007, the hub height is reached about 100 meters. And the diameter, look, the diameter of the tower is increased significantly also. It would be arose a lot of structural problem to the structures like towers. As we all know, the most commonly used tower in the offshore wind field is a tubular steel tower. With the diameter and hub height increase, a lot of structural problem, especially the shell buckling problem, is increased gradually. So it arose a lot of problem like this kind of failure, buckling failure. Some professor present a new concept of hybrid structure of tower like that. Substitute traditional steel material with hybrid material in some location of tower. Consider this kind of concept. We do detailed research on the new hybrid material, Malecon. As we all know, micro hybrid material, Malecon, the same as a lot of composite material. It has a lot of expected benefits. For example, corrosion fatigue resistance, lightweight, and high stiffness. Especially adverse environment adjustment is very important to the offshore industry application. Then the high stiffness, strength, and lower cost, corrosion resistance, all these kind of benefits, like Malecon or that kind of hybrid material, has a lot of opportunities to be used in offshore industry. Some successful applications like the top set of oil-filled, top set of jacket, oil-filled structure, and some panel structures and some risers already have some successful application for the composite material. The material we talk today is Malecon. Malecon is a patent hybrid metal hybrid material of UPM. The basic concept of Malecon is a steel layer. Steel layer combined with plies of E+2, and the E+2 adhesive to the outer layer by structural adhesive. And the Malecon can be that kind of set steel layer with numbers of E+2 and 3 layers of steel with numbers of E+2. The E+2 is a package of layers of hybrid materials. It was composed by mud material and fiber reinforced material like this one, that one, and core material. The detailed property of that layers is eliminated for the page requirement. In analysis ways and means, I use benchmark examples. The first one is simple panels. The panels is that kind, simply supported panels. And there are 3 kinds of load case. The first one is uniform load case. The second one is a kind of axial compression, axial compression in X direction. The third one is elastic tensile load. We use this kind of three load case to illustrate the properties of the material Malecon. In panel examples, we suppose four kinds of Malecon. The first one is Malecon 1A. There are two steel layers with one layers of E+2. And the Malecon 1B, there's two layers of E+2. And the Malecon C, we use three layers of steel. And the Malecon D, we increase the layers of E+2 between the steel. So there are about four kinds of Malecon configurations we used in panel benchmark examples. Then the second example is a kind of tower examples. The monosteel cylinder cross section tower is that kind. Totally, there are three kinds of parts. The part one is composed by 8 plates with that kind of thickness, and part 2 with 12 plates with that kind of plate thickness, and part 3, the top part of the tower, is composed by that kind of steel thickness. The diameter of the tower is tapering from the diameter 4.274 to the top diameter is that kind of 3 meters 2 meters 0.345. So the model is a kind of a tubular tower tapering from the bottom to the top. This type of structure is commonly used in currently obsolete converters tower. So we use this model as a benchmark. Then we try to analyze the Malecon property. So the Malecon material we use here is that kind. 2 steel layers with numbers of E+2. We add the numbers of E+2 to compare that kind of Malecon towers and the benchmark Malecon steel towers. So steel towers is our target, and Malecon towers we change the E+2 number to try to let these two models have the same kind of mechanical property. The software we used for panels, we use Sfcm software. Sfcm software is a software especially for the composite material. We just need to define price in the database, because E+2 have that kind of layers, adhesive, steel, and mud. TEJ-E and UNI-E is a fiber-enforced layer, and the mud and the core material are in the E+2. And steel layers, we choose outer layer and the bottom layer. Both these layers and steel are combined by structural adhesive material. We define laminate with that price, and we define plate with that kind of laminate. We get that kind of place, and we analyze uniform load case, and buckling load case, and the tensile load case. So 3 load case in the panels. As for the tower model, we use Abacus software. We define the Malecon use composite cell element in the Abacus, and we constructed steel models and Malecon models together to compare the different performance of steel models and Malecon models. I will talk the results later. Okay, this is the panel simulation results. In order to get the detailed performance of the material, we define some parameters. The first parameter is a FME. Look, FME is a ratio of steel panels to Malecon panels. So it's an air density ratio, FME. RCF is a price ratio of steel and Malecon. CRF is a correlation index of air density and price. So CRF is the result is FME plus RCF. So the first parameter is concerned for the density or for the weight of structure. The second parameter is concerned on the price. And CRF is a comprehensive parameter to get the detailed performance of the material on the weight and the price. This is the result. This is the result of uniform pressure load case. So for pressure load, we get that kind of result. FME is let me say, FME is a density ratio. So let me see the result. OFME for Malecon 1A, 1B, 1C, and 1D are all about 1. All about 1 means steel is heavier than Malecon model. So Malecon model is lighter and it's better. This is for steel thickness and this is for metal volume. The metal volume I will talk to you here. The metal volume means the metal thickness divided by the total panel thickness of Malecon panels. So from that picture we can see Malecon panel is better than steel panel because it's lighter. The second parameter is price ratio. The price ratio we can see all the results is lower than 1. So unfortunately, even Malecon is better in weight, but is much more expensive than monosteel. The fabrication cost of Malecon is heavier, or maybe it's more expensive than monosteel. But what matters is the comprehensive result. Let me see the comprehensive result. Comprehensive result is the weight and price considered together. You can see these two lines, the green one and the red one, is still about 1, and that two lines is lower than 1. So we can say even Malecon is a little bit expensive than steel, but take consideration of the weight contribution. There are still two kinds of Malecon is better than monosteel. These two kinds of Malecon is that one. Look, that one is Malecon 1B, and that one is Malecon 1A. So with Malecon 1A and Malecon 1B, that kind of configuration, Malecon material is still efficient than the monosteel structure in panel case. This is the result. In order to illustrate it clearly, we use only one Malecon B to clear the above results. Look, this is the Malecon B density ratio. For Malecon B density ratio, we can see Malecon 1B is better than monosteel because it's lighter. And for RCF, Malecon is no better because it's more expensive. But for the comprehensive parameter CIF, it's still better because it's about 1, and in that kind of range, in that kind of steel thickness volume range, around 0.3 Malecon, this is the most efficient range of Malecon material for panel benchmark models in uniform load case. Okay, in that kind of idea, with further analysis, Malecon with that kind of parameter in vacuum load, in H vacuum load case. Look, BME is the density ratio and RCB is a price ratio. CIB is a compressive index also. The same idea with about uniform cases. Look, this is the result. For BME, for density ratio, all Malecon is better than monosteel because the result all about 1. And for price, it's still no good because all Malecon is much more expensive than monosteel. This is the result of the Malecon material in vacuum load case. We can see there are still 2 lengths about than 1. So there are Malecon 1A, Malecon 1B are still more efficient than monosteel. From the result you can see. And the other to clarify the result, we use Malecon B for simple example in one picture. This is BME. In vacuum load case, Malecon B is better because it's lighter. And Malecon B, the fabrication price is Malecon B is no good because it's expensive. But the comprehensive index around 0.3 to 0.4 of micro volume, the Malecon 1B is still efficient than monosteel panels. So in vacuum load case, we get the same results with the uniform load case. The third load case we consider is the tensile load case. We use the same kind of parameters. This one for density compare. This one for price compare. This one is a compressive parameters. Look, the result is not the same as above result. For simple tensile results, for simple tensile load case, even for the density, Malecon is not good as monosteel because even they have the same tensile strength, but Malecon is a little bit heavier than monosteel. And the result is the same. The price, the fabrication price of Malecon is much more expensive than monosteel also. And the comprehensive result is no good also. This is the one picture for Malecon B in tensile, elastic tensile load. Assuming they have the same kind of tensile load with monosteel, Malecon is heavier and more expensive than monosteel. So in tensile load case, Malecon is not a good substitute material for monosteel. Following is a kind of comparison of steel and Malecon panels. Firstly, we set an example. Steel panels with thickness of 20 millimeters. And we let Malecon have the same kind of flexural rigidity with the steel panel. So then we constructed, then constructed the configuration of Malecon. E+2 is a constant, and we change the steel thickness to that numbers, and we got the same kind of flexural rigidity. So did the 1B, 1C, 1D. E+2 is a constant material, and we set in different kind of thickness of steel layer. When the steel layer of Malecon reach that kind of numbers, these models of Malecon have the same flexural rigidity with the steel models with thickness 20. And that is the volume of steel thickness in Malecon material. So we set that kind of examples to compare the different performance of Malecon models to the steel models. Look, this is the result. Because they have the same kind of flexibility, Malecon steel has the same deflection, the maximum deflection, with the Malecon material have the same values of maximum deflection with the steel. And the result, we got the same buckling load with the steel also, but we got the different kind of tensile strength in that numbers. Look, Malecon with the same steel thickness, we still can reach the same flexural. They can reach the same maximum deflections and the buckling load, but with lower tensile strength. This result is the same with above analysis. And this is the weight analysis. For the steel models, the overweight of panel is that kind of value. And for Malecon A, B, C, D, we have the same kind of maximum deflection, but with lighter weight. Look, we have lighter weight, and we use parameter FME to compare it also, because when FME is above 1, means Malecon is lighter than mono steel. Look, the above one may be that one, Malecon B, and Malecon B, the value is much more above than 1. It means this material is much more lighter than mono steel. We continue to compare FME, RCF means take consideration of fabrication cost into the property of the material, and get the CIF. We got the same result also. Look, this is FME, this is RCF, this is CIF, and different. Look, A, B, C, D, we saw for density, this one, Malecon 1B and Malecon 1B is better. And for RCF fabrication cost, even this one is lighter, means, but this one is much more expensive. So it may be not good. This is the comprehensive result. For the comprehensive result, we can see only this one and that one about 1. Means Malecon A and Malecon B is more efficient in panel case. The same kind of result is plotted in this picture. This is a panel case. If we take consideration of buckling load and the tensile load together, look, for the same flexural rigidity, they can reach the same kind of buckling load. So RB is 1 also, but Malecon is no good than mono steel in tensile load because RT is lower than 1. If we take RB and RT together, we use the same kind of ways. Use that parameter, we can get CRF Gang RB means take working load condition into consideration, because RB is 1, so the result is the same with the flexural load case. If take RT into consideration, because RT is lower than 1, we can see all Malecon for tensile load case is no good, but relatively Malecon 1A is better, because Malecon 1A is much closer to 1. So this is the analysis ways for panel case. The result for the panel case a little bit like that. The composite panel of Malecon, deduced by assuming the same flexural rigidity, can obtain the same buckling load as steel panels with relatively lower volume of steel. As for the elastic tensile strength, Malecon panel is lower than steel panel is no good. The composite panel of Malecon deduced by assuming the same flexural rigidity, so good property of lightweight than ductile steel. They can reduce weight by 27, 42, 30, 35, and almost 50% than the mono steel. But the fabrication cost of Malecon is a little bit higher than mono steel. You have to pay that kind of much more price for the Malecon structure. Take consideration of both mechanical and economical factor into consideration. Malecon B and Malecon A is much more efficient in buckling and flexural load case. Well, if the structure would undertake a kind of consideration tensile load, you must take care to substitute the Malecon material to the mono steel. This is the result of the panel for the Malecon. The second benchmark example is for the towers. We set example, this is the benchmark towers. It composed by 3 parts. Firstly, we set the lower parts, the bottom parts of the tower as an example. In order to get the top edge buckling load case, we set clamped constraint, load constraint conditions in that. This is a mono steel part 1. This is a Malecon part 1. For the Malecon part 1, we use 40, 50, and 60 steel thickness. Means we take the Malecon steel layers T from the tower top of mono steel layers. We already talked. The mono steel the mono steel diameter, the mono steel thickness of the part 1 is 26 millimeters. As for Malecon, we take steel layer of that kind of value to get the configuration of Malecon. In order to like that two structure have the same kind of mechanical property, we add the numbers of E+2. We use this way to compare that kind of two structures. And this is the result. Look, for X labor is the numbers of E+2. For the Y is the buckling load of the top edge. From that result, we can see the right one is a Malecon with 40% steel layer of bottom of part 1's mono steel thickness. and that is the 50, and this is 60. So this is the Malecon structure, and with numbers of E plus increasing. From that result, we can see for the right pictures, Malecon with 40% of steel thickness. When the numbers of E plus 2 reach 4, the vacuum load is higher than monosteel, because this dashed line, black dashed line, is monosteel structures vacuum load case. So that one, the number is 3, that one, the number is 2. The Malecon would be have the higher vacuum load than monosteel examples. From that result, we can see when we reach the numbers of E plus 2, we can let Malecon material have higher vacuum load than monosteel. And this is the mass comparison. That one is the monosteel part 1 mass. This is the kind of second examples. And we reach the numbers of E plus 2. We can see when the number reach that one, maybe 9 E plus 2, this model would be heavier than monosteel. From this picture, we can see the Malecon can, the mechanical of Malecon can be better than the monosteel in that kind of numbers of E plus 2 with still lighter thickness, with still lighter weight. Okay. This is the ratio comparison. That's X still number E plus 2. That one we set a ratio. The ratio is the Malecon. The ratio is the, look, we define the ratio buckle, ratio mass here. In that case, the ratio is Malecon to monosteel vacuum load ratio. We can see that one. When we reach that kind of number is about 1. So Malecon can be, Malecon structure can have about a vacuum load case than monosteel, still with lighter weight. And this is the vacuum load mode of the structure. This is the vacuum load mode structure, and that is the vacuum load mode structure. We can see that kind of result in the following analysis. The second analysis, we set part 1 and part 2 together with the same kind of load with the same kind of constraint condition, and we compare each vacuum load also. The same kind of Malecon material configuration. This is the result. This is the result of vacuum load comparison. We can see this is the monosteel part 1 plus part 2, and this is the Malecon with different kind of steel thickness. We can see for Malecon, when the numbers reach 2, 3, 4, and it can be above the monosteel part 1 plus part 2 structure, and still in a kind of lightweight effective range. The most difference about that picture, we can see the trace. When we keep increasing the numbers of E plus 2, the line is not keep increasing. It's a kind of that way. It means even we increase the number of E plus 2, we cannot increase the vacuum load of structure gradually or the same way like that range. Let me consider that kind of problem in the following picture. Look, this picture, from that picture, we use the ratio of buckle. Compare ratio of buckle and compare ratio of mass also. And this is the dash line. This dash line is 1. 1 means Malecon is equal to monosteel. But when the number is 2, 3, 4, the buckling load of Malecon is above than the monosteel. Look at mass is still lateral. So Malecon substitute for part 1 and part 2 is still efficient. But when we keep increasing the number of E+2, even the mass is increased the same as above cases, but the buckling load is not increased gradually. Let me see what kind of result. For that one, the buckling mode is still kind of shell buckling. But for that one, the buckling load is changed from shell buckling to typical column buckling. So the typical column buckling, for that kind of case, Malecon may be not effective. Further results with models with part 1, part 2, part 3 together for monosteel, and the models is part 1, part 2, part 3 for Malecon. It means we substitute all the tower with Malecon structure, with different numbers of steel thickness and different numbers of E+2. Let me see the result. For the buckling load, this is the tower's monosteel tower buckling load sample. We can see, even we reach E+2 from 1 to 10, all the Malecon buckling load is lower than monosteel. And the mass of Malecon models would increase gradually, and finally would be much weightier. The weight would be higher than the monosteel structure. So in that case, even we increase the E+2, we cannot reach monosteel buckling load. But the mass of Malecon would finally greater than the monosteel. Okay, let me see the ratio picture. This is the ratio picture. We can see this line is mass, and that continuous line, look, continuous line is buckling ratio, and the dashed line is mass ratio. We can see with increased numbers of E+2, the mass will be increased gradually. But the buckling load always, although the buckling load increase, but it still cannot reach the monosteel value. In that kind of value, in that kind of case, we take that two case to take out the model shape. We can see in that case, all the model shape are typical column buckling. So from that result, we can get that for the typical buckling load failure, Malecon is not efficient. But for the shell buckling, Malecon can contribute a lot. This is the result. Buckling load of Malecon only substitute for part 1 with different steel thickness percentage. This is the steel thickness in the layers of steel thickness in Malecon, and this is the thickness of monosteel. We get that value by that kind of percentage to that value. And in this case, we can see buckling load for Malecon only substituted for part 1. Malecon is better than monosteel because when the E+ number reach 432, Malecon can be reach the monosteel buckling load with lighter weight. And we substitute to part 1 and part 2 to towers. We can get good results also because Malecon, when the number reach 432, Malecon can get the same kind of backing load with lighter weight. But we cannot keep increasing the E+2 because when the model shape is changing from shell backing to the typical column backing, the Malecon is not efficient as only part 1 substitution. The final one is substitute Malecon for total towers, means part 1, part 2, part 3 together. We cannot get efficient range for the Malecon structure because even we increase the number of E+2, the mass increase gradually, but the backing load is not increased. It cannot have that kind of range with the same kind of backing load but lightweight. Yes, from that kind of analysis, we can get that kind of result. Malecon can be successfully used for panel structures because for panel structures, it can provide savings in weight and fabrication price together from the parameter studies. But for tower structures, optimal analysis must be done because in different parts of structure, Malecon contribute differently. From our results, we can see the bottom part of towers is an efficient choice for Malecon material substitution. All these are the current results. Thank you very much.
Thank you very much. We have time for some questions. No, I have a general question. What is the future? What is the limit for this kind of structure?
Yes, from our analysis, we can see the type of offshore wind turbine towers is large diameter with large diameter. The larger of diameter, the Malecon would be more efficiently, and the efficient part would be the bottom part of the tower, not total tower.
Thank you very much. Well, thank you for your presence here and for this very interesting talk. And you are welcome if you want to return in the future.
Okay, thank you.